Alright, football practice. You're helping a football team perfect a certain play in which the thrower Theo and the receiver Reggie are trying to link up on some long 60-meter pass. At the beginning of the play, i.e. at t equals 0, Theo and Reggie are 60 meters away from the end zone. They're at the same spot, standing 60 meters away from the end zone. And Reggie runs in a straight line towards the end zone in the following sequence. So obviously this part is going to be talking about Reggie, and then looks like this part, as soon as Reggie starts his run, Theo does something else, right? He's gonna throw the ball. So we're gonna break the problem into a Reggie problem and the Theo problem, and they're related somehow. So we'll start with the Reggie piece. What does Reggie do? First, he accelerates from rest to his top speed of 8 meters per second at some constant rate, 2 meters per second squared. Then he maintains that top speed for the rest of his run to the end zone. So his run to the end zone has two segments to it. One segment in which he accelerates from rest to some top speed, and then he maintains that top speed at a constant speed for the rest of his run to the end zone, right? So if I start with Reggie at rest right here, so this is Reggie, and he's standing at rest at t equals 0, and I'm going to call this point x equals 0, and then he's going to end up in the end zone at some point which is 60 meters away. This is going to be in two segments. So in the second segment, in the step in between, he's going to get from here to this first. The first segment is going to be him accelerating a constant acceleration of 2 meters per second squared, and until he gets to a velocity of top speed 8 meters per second. And this is at rest, so 0 meters per second. Okay, so I parsed that first part. He accelerates from rest to his top speed of 8 meters per second at a constant rate of 2 meters per second squared. So this first leg is done. Then he maintains that top speed for the rest of his run to the end zone. So then he's at constant velocity because his speed is constant and his direction is constant until he gets to the end zone where he catches the ball, I guess. So I'm going to call this the end zone. And the end zone is 60 meters away. And throughout here is constant velocity, which is equal to the top speed. So I've taken all the information from that piece and I've drew it. Now, as soon as Reggie starts his run, Theo counts 3 seconds, then throws the ball to the end zone, assuming no air resistance and that Reggie catches the ball at the same height it was thrown. What is the velocity? So for Theo, his kinematics are described, or I guess the kinematics of the ball really, but represented here by Theo, is that he holds the ball for a bit from t equals 0, and then he waits for 3 seconds, and then Theo is going to throw the ball some initial velocity v naught that's going to have some x component and some y component. okay? And this is t equals 3 seconds. And here is x equals 0 still. And then he throws the ball, and that ball is gonna be caught at the same height it was thrown. So y equals 0. And I'm gonna make this choice that these are my positive directions for x and y. Okay? And of course, the only thing that's affecting the ball in the middle is the acceleration of gravity. And this is minus 9.8 meters per second squared. So assuming no air resistance, that means this is the only thing. And that Reggie catches the ball at the same height. So this is y equals 0. What is the velocity with which? So really what I want to know is v naught. Okay, the following sequence of questions will guide you to the answer. So let's answer one of these questions at a time. Okay, the first question is, how much time does it take Reggie to reach his top speed? So essentially it's asking about, to get from here to here, what is the time? From rest to his top speed. So what do I know about that? Well, I know that it's constant acceleration at 2 meters per second squared. I know that he starts from rest. And I know that his final speed is 8 meters per second. I don't know the time, and I don't know the distance. But here's just asking about the time, so let's figure out which equation I can use to figure out the time. And I think the best one for this case would be v equals v naught plus at, which means that 8 meters per second is equal to 0 plus the acceleration times time, which means that the time is equal to 4 seconds. So for part B, we're still talking about the same part of the same segment for Reggie. Here we're asking what distance does he cover to reach that speed. So from here to here, what is the distance? We found out what the time was, same kinematic variables. We want to know what x is. And in this case, really I can use any of the other three kinematic equations. Maybe I'll use all three just to demonstrate how to do that. So for example, I could use x equals v naught t plus half at squared. So v naught is 0, t 4 seconds, doesn't matter, this is 0, half 2 meters per second squared times t squared 4 seconds squared. Half of 2 is 1, 4 squared is 16 meters. I also could have used x equals to the average velocity times time. So v naught plus v times t. And in this case, v naught is 0, so it's half 8 meters per second times time, which is 4 seconds. Half of 8 is 4 times 4 is also 16 meters. I'm glad it comes out to the same thing. Or I also could have used, what's the last equation? It's the one where you have the v squared minus the v naught squared over twice the acceleration. V is 8 meters per second all squared, minus v naught squared, that's 0, over twice 2 meters per second squared. So 2 times 2 is 4. 8 squared is 64 by 4 is also 16 meters. So any of these really could have worked. Then the second piece is asking how long does it take Reggie to cover the rest of the distance to the end zone? So the rest of the distance meaning from the point he reached the top speed to the end zone. So now in this case, I want to find out what the kinematic variables are. I can write them down. Acceleration, it's constant velocity, so acceleration is 0. And he starts out at 8 meters per second. He stays at 8 meters per second the whole time. And the time is what we don't know. And the rest of the distance is, well, we don't know it, but we can find out what it is. He travels 16 meters, and then the rest of the distance then would be 60 minus 16, so that's 44 meters. So really, I know everything except time, so I can figure that out. And the simplest way, really, I would say, is to use the average velocity, or you know, distance over time is equal to velocity, or something like that. So I would say, for example, x equals half v naught plus v times t. Therefore, t is equal to x, which is 60 meters, divided by the average velocity. These two are the same, so twice v over 2 is v, so 8 meters per second. 60 over 8 gives me, oh, sorry, it's not 60, of course it's 44. It's the rest of the distance. 44 over 8, 40 over 8 is 5, and 4 over 8 is half, so it's 5.5 seconds. Okay. And then the last part about Reggie's kinematics is asking what is Reggie's average speed from the beginning of the play to the moment he reaches the end zone. So the average speed is a scalar that has to do with the scalar, which is the distance, total distance covered over total time elapsed. So total distance covered is the 60 meters. The total time is the 5.5 seconds from this piece and the 4 seconds from this piece. So he covers this part in 4 seconds, this part in 5.5 seconds. So the total is 9.5 seconds. So 9.5 seconds in 60 meters gives me something that is slightly bigger than 6. There's a half. So half, 6.3 meters per second. Okay. Cool. Now, let's see what happens to the ball. The ball and Reggie arrive at the end zone at the same time. What is the total time of flight of the ball? Of course, Reggie takes 9.5 seconds to get there. So, flight of the ball, flight time, is the 9.5 seconds that Reggie takes minus the 3-second wait by Theo before he throws the ball. So it has to be 6.5 seconds. For them to arrive at the same time. What is the horizontal component of the initial velocity of the ball? So I have to think now this is a 2D kinematic problem. It's a projectile problem. in which I can write the x components of the kinematic variables. I know that x is the total distance, 60 meters. That's the range of the ball, the flight of the ball. I know the initial velocity is something that I don't know that I'm looking for. And if I knew it, I would know this one as well. I know that there's no acceleration in x. And the total time of flight of the ball, I know that. I just calculated it. It's 6.5 seconds. Knowing that a is 0 tells me that these two things are equal. V naught x is equal to Vx. If I want to find out what they are, I could use, for example, this equation. X is equal to V naught t plus half at squared. This equation is nice in this case because the acceleration is 0, so this term is going to cancel out. So that means that 60 meters is equal to V naught x times the 6.5 seconds. That means that V naught x is 60 meters over 6.5 seconds, which is 923 meters per second. Okay, so that's the x component of the velocity. What is the vertical component? Then we got to separate the variables. We write the y variables. The only thing that's common between the x and the y is the time. So it's the same time of flight of the ball, 6.5 seconds. Ay I know is gravity. V naught y and Vy we don't know. We know they're going to be opposite of each other in terms of sign, but we don't know what they're going to be. I know that they're going to be opposite of each other in terms of sign because in all the problems that we solved, when you go from one height, you go all the way and you come back to the same height. It's the same velocity in y, but in opposite direction. And I know that it's going to come back to exactly the same height because Reggie catches the ball at the same height it was thrown. So if I know this, that means I can use, for example, the same equation that I used for x. I could use y is equal to V naught y times time plus half ay t squared. I know that y is 0. V naught y is something I don't know. T is the 6.5 seconds. And I fill in the rest of the variables. I sub in for the rest of them. Now this means that V naught y is equal to this piece. So half minus 9.8 meter per second squared multiplied by 6.5 seconds all squared over this piece with a negative sign. Right? Imagine that I moved all of this to this side. So subtracted this from both sides. That means it'll be with negative sign here, and it'll go away from this side. And then I divide both sides by minus 6.5 seconds. Okay, the minus will go with the minus, so that's good. And then the 6.5 seconds is squared on this side is going to go with the 6.5 seconds here. So I'm left with 1 6.5. So I know then that this will be half 9.8. So that means it's 4.9 times 6.5. So I'm left with 4 meter per second squared times 6.5 seconds, and this turns out to be 31.85 meters per second. So I've calculated the x component of the velocity, the initial velocity, the y component of the initial velocity. I can combine these two to combine the velocity components to calculate the magnitude and direction of the final velocity. So I know that the x piece turned out to be 9.23 meters per second, and the y piece turned out to be 31.85 meters per second. So I know that the velocity will be given by the Pythagorean theorem, and I know I can calculate this angle. So the velocity is the square root of 31.5 squared plus 9.23 squared, and the angle is the arctan of 31, the opposite over the adjacent, 3185 over 9.23. This one will be square root of 1100, which is roughly 33. And this one will be 74 degrees. And this concludes the calculation for this question. What's the only thing that's left is to do the graphs. So for the graph piece, we're asking, we gotta plot the horizontal and the vertical parts of the velocity versus time for Reggie and for the ball. So for Reggie, I know that he's gonna run the 60 meters in 9.5 seconds. So let me see, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I have 21 squares, so I guess I can do half a second for each square. So this is 1 second, 2 seconds, 3, 4, 5, 6, 7, 8, 9, 9.5. This is the end of play. We know that he accelerated for 4 seconds. He accelerated up to 8 meters per second. I know that for the ball, the x velocity is also about 9. 1, 2, 3, 4, 5, 6. So we'll take 2 meters per second, 4, 6, 8, 10. For the first 4 seconds, he accelerates up to 8 meters per second. That's Reggie. So Reggie goes in a straight line like this. Because it's constant acceleration. So for v versus t, constant acceleration is a straight line. And the slope, of course, of this line is the 2 meters per second squared. And then after that, he goes from the 4 to 9.5. He goes at a constant velocity. So that's Reggie. In the x direction. As for the ball, we know that Theo waits for 3 seconds. So basically the velocity of the ball was 0 for the full 3 seconds, the first 3 seconds. So from here to here, the velocity of the ball was 0. And then he launches the ball at something like 9.23 meters per second. So that's roughly here. So the velocity starts from there. And the velocity is constant for the rest of time until it gets caught, because there's no acceleration in x for the ball. Okay. Now for the y component, Reggie is easy. Reggie doesn't jump or do anything in the y, so Reggie is just going to stay for the 9.5 seconds, is going to stay at 0 throughout. So we'll plot it anyway. As for the ball, I know that its maximum velocity is around 32. So say 1, 2, 3, 4, 5, 6. So I'll say each one is 5, 5, 10, 15, 20, 25, 30. And I know that for the first 3 seconds, the ball has no y velocity. So it's also going to be 0 for the first 3 seconds. And then it's going to be launched at 31 meter per second square. Meter per second. This is the ball. It's 0 for the first 3 seconds. And then it's going to have a vertical component of 31 meter per second, 31.85. And then it's going to be launched against gravity. The only thing that's acting on it is gravity. So that velocity is going to start slowing down. As the ball is going up in the air, it's going to start slowing down until it reaches 0. And then its velocity is going to flip and it's going to be negative. And then it's going to start speeding up as it's going down. And the slope of this line is the 9.8 meter per second square. This is the slope of the acceleration of gravity, right? Because we said the slope of v versus t is gravity. So again, it's 5, 10, 20, 30, roughly around here. And it's just a straight line from here to here. Right? And I expect this to be right in the middle between 3 and 9.5. And I expect that this is going to be minus 31.85 meters per second, because the velocity of the object when it's at y equals 0, when it's going up, it comes back down with the same velocity and at the same magnitude, so the same speed, but the opposite direction of velocity. So that's why it's a minus 31.85. And this concludes part B.